I got time. I don't have to do it right now. What's your maintenance window? What's your patch window like? When there's something new that comes out, maybe for Patch Tuesday, how long do you have to get that system patched? What do you got? 3 days. Whoa, man, good for you. That's aggressive, 3 days. Man, I've got a customer, they're at 7 days, and I thought that was awesome. 3 days? That's fantastic. Is anyone higher than 3 days? Yeah, 2 weeks, 30 days, yeah, 3 weeks, whatever. I mean, 3 days, well, good for you. But most people, no way. Let's talk about that problem. Because, you know, there's resistance to patching sometimes. And what I'm talking about, I abbreviated here, MTTR, mean time to repair. What's your mean time to repair? And we're going to use as an example of this something that happened last year. Last March on the 13th, Microsoft says, hey, there's a vulnerability in RDP, and it's going to be bad. Because without any credentials, it is possible to take over a Windows box and get it to do arbitrary stuff remotely. That sounds pretty bad. And Microsoft releases this out-of-band patch. You're urged to patch quickly. Now, first of all, we know there's resistance to patching. Why? Why is there resistance to patching? It breaks things. In fact, especially for Microsoft, it seems, they are the worst at this. Their patches seem to break half their stuff. I've got a customer that was deeply invested in SMS with Mom, and you know what? You know why they killed it? Because every time they applied a Microsoft patch, it completely broke their Mom infrastructure, and they had to go reinstall all the agents. It's their own product. So there's definitely resistance. But there's another big reason. Hey, I got 30 days to get this done, or 2 weeks, or whatever you got. I got 30 days to get it done so that I can test it, make sure it's all going to work. When does that testing start? Be honest now. The managers aren't here. Day 28, yeah. We start thinking about, oh yeah, that patch window's coming close. We better start testing this thing. And then we're maybe going to get it applied on the 30th, or on the 30th say, hey, listen, testing showed it doesn't work. Now, we could have known that 20 days before, but we didn't start yet because, you know, we work right up to deadlines. Then there's this other problem that they involve work, the testing and patching and all that stuff. It's work. So these are definitely resistances. And then there's this thing that, well, heck, we're not running that, so I don't have to worry about it. Or it's not facing the Internet, so I don't really care about that, you know. I was talking to a class earlier this week. As a pen tester, do you know what the #1 vulnerability we find inside of networks after we're inside? So not from the outside, but once we've got something inside. You know the #1 vulnerability? MS08-065. MS08. What does 08 mean? 2008 patch. MS08-065. #1 thing. If I get into a network and it's got more than a couple of hundred hosts, there's going to be something vulnerable to that. Because, well, it's not on the Internet, don't have to worry so much. And this idea of we're not running it. So you've heard of this cloud thing, right? The cloud. And we know cloud means, really, I have no idea where my stuff is. We know that's what it actually means. But besides that, we've got all this infrastructure and platform stuff we're doing in the cloud, which means that there isn't a physical console for me to go touch. So how are you administering those cloud-based things that you're paying for? Well, you're using stuff like RDP and Secure Shell and stuff. And you know, there are major infrastructure providers, cloud-style providers, that what they're selling you is maybe an ESXi instance, and the management interface for that thing, you know what it's connected to? The Internet. That's how you control it. And so now you stand up a Windows domain controller and you connect it to the Internet because that's how you control it. So we actually have these all over the place. It's actually kind of disturbing. H.D. Moore does a lot of scanning of the Internet. You may or may not have heard of him. He actually is the original author of one of the tools we'll look at here. And he usually rents space in Russian servers to do his scanning because, you know, they don't get so upset in Russia when you scan stuff. And he's got some phenomenal statistics on how many RDP servers and everything else you'll find on the Internet. It's disturbing. And then there's this thing that, well, there aren't any exploits out yet. And even then, if you knew the details, that would be really hard to do. And that's what we want to examine. How hard would it be? Well, March 13th, Microsoft makes the announcements. March 15th, hackers in China say, we've got proof of concept code that can demonstrate the flaw. So have you patched yet? Now, we're still inside your patch window, right? We're at 2 days. Later that afternoon, working exploits observed in the wild. We're at 3 days. Are you patched yet? Are you patched today? Well, I hope you're patched today. But see, that 30-day window, man, there's a lot that can go wrong. And by the way, when Microsoft issues you an out-of-band patch, I know the party line is, well, there's no exploitation in the wild. If that's true, why aren't they waiting till Patch Tuesday? Why are they issuing it out of band? Because it is seen in the wild. There's been compromised stuff. It's a really big deal. Well, let's examine this a little bit. Let's see. We want to talk about this idea of how hard is it? Not there's already a Metasploit module or some other thing that I can run and exploit. I mean, Microsoft announces there's a problem in this service. A security researcher or a hacker hears that and says, well, I'm going to go figure out what that thing is. And often the information they give you, it's not enough to just go do it. You have to go test that thing out and figure out what the flaw is. So we want to see how hard is that? Because the myth is that it's hard. Let's check that out. And our plan is that we are going to do it in 60 minutes or less. Now this, of course, this is like coming into a SANS conference and juggling chainsaws, because there's all kinds of ways this can go horribly wrong. But we'll do the best we can. Let's see how we do. To do it, we are going to do some demonstrations and stuff, but first, we just want to lay some groundwork about what our research will look like. I'm not going to work on the RDP flaw. That's going to be too complex for us to talk through in 60 minutes. I'm going to do a different demonstration, but it's illustrating the same kind of thing. There's some service we've heard of, and there's some flaw in it, though they haven't been real specific about it. We're going to do our research on that. The research we're going to do is going to involve an overflow flaw. Now, overflows are actually super easy things to understand. In fact, I've got a friend, two friends, a couple, Ron and Luce, and when Ron and Luce got married, Ron, he already knew that Luce, she had a little bit of a shoe addiction. So before they got married, he made her, as part of their engagement, as an engagement present, he made her, he's a Finnish carpenter, this beautiful shoe rack. It's got all these little cubbies in it. It's really, really pretty. And it can hold 64 pairs of shoes, because she's got a little bit of a Melda in her. She likes her shoes. Well, anyway, the deal was, when we get married, you can have as many shoes as you can fit in that shoe case. What happens when Luce gets pair number 65? It's going to have to sit on the floor, and he's going to have to build another shoe case, because he's not going to make her get rid of them. But see, it doesn't fit in the case anymore. The case is now overflowing, right? You fill the glass with water. What happens when you put a little more in? It overflows. I mean, it's not a tough thing. In the memory of our computers, we've got memory areas that get allocated for stuff. I'm happy you've got 16 gigs of RAM in your laptop. But when that program allocates a buffer, it doesn't matter you've got 16 gigs. That buffer's only this big. And if you put more in there than you're supposed to have, it's going to overflow. And if it overflows, where is it going to go? It's not going to land on the tablecloth. It's going to overflow into the other memory. It's going to start overwriting stuff. We're going to be taking advantage of that. In particular, we're going to be taking advantage of a stack overflow. We're going to work with stack overflows because they are conceptually easy, and there are lots of things that involve stack overflows. This actually doesn't, I don't want to imply, though, that exploiting other things is a lot harder. It's not that. Exploiting other things is really no harder. It would require a lot more time for us to explain how those memory structures work, and I don't want to do that. So we're going to stick with stack overflows because it's an easy concept to understand. The stack is actually a pretty important thing. And even that name is pretty easy, a stack. Imagine you were working in a restaurant. You were a dishwasher. So there you are sitting at the back. You're at the sink. And what's next to you on the sink? A stack of plates. Which plate are you going to wash first? You're going to lift all those plates up and take the one from the bottom, right? No. You're going to take the plate off the top of the stack. When the waiter comes in, he drops off some more plates. Where's he going to put them? On the top of the stack. And you're going to work your way down one at a time. It's called a last in, first out queue. It's a memory thing. But it's a stack. I mean, we can relate to that. It's a stack of stuff. In your computer, in programs, with the kind of computers we use, now there actually was a competing design for computers in the 50s that lost. And the kind of systems we all use the stack-based approach for managing stuff. And the stack is used as a temporary holding area. Like I'm reading through a book, and in the book, there's a word I don't really understand, but the back of the book has a glossary. So what would you do? Wouldn't you maybe hold your place in the book, flip to the glossary, look up the word, and after you got the word, what are you going to do? Go back where you were. So your hand is like a bookmark, right? Well, in the program, that kind of stuff's happening all the time. It's not looking up a word, though. What's happening is the program's executing, and then it gets to a point where, oh, I want to print something on the screen. Well, there's a function that does that. So it puts a little bookmark on the stack, goes and prints something on the screen, and then looks on the stack and say, oh, okay, that's where I go back to keep running. So we do this kind of thing all the time. It's also used for storing local variables. You're going to see it in just a second, in fact. Let's take a look. Let's imagine that we had a piece of code. It is not complex code. In this code, we've got a little function over there, the main function, the thing that will actually start, and it defines a little character array containing 2 characters. And after that, it calls a function. It calls printf, and printf is going to try to print whatever comes from getInput. Well, look at that. It's a function up at the top there. Now, getInput is a horribly insecure function. Yes, I know. Just for demonstration purposes, don't go do this. It's bad. And all it does is ask the user to enter in some stuff without doing any checking on how big the stuff is, and sticks it into a buffer that's 16 bytes long. So even if you're not a programmer, can you kind of see that's what's happening here? Now, what does that look like on the stack? Well, you see, there's this memory structure, this stack, that is like that stack of plates. And this stack typically resides toward the top of memory within a process space. Now, this is the weird thing, the really weird thing. When we've got our plates on the counter, we start at the bottom and work our way up. So the top of the stack tends to be up here, and the bottom is down there, right? That makes sense? Imagine the gravity reversed itself. Your plates are now stuck to the ceiling. That is essentially what happens here. So the stack, you see on the left-hand side, I've got these big hexadecimal numbers. Those are memory addresses. And I've chosen to make my stack 4 bytes wide. Now in memory, it's not really wide. But what's happening in most stacks is the smallest thing you can stick on the stack is usually 4 bytes wide. In fact, if you tried to put just one character, 1 byte, onto the stack, it would push that character on along with 3 nulls, because that's the smallest thing you can put there. It's pretty typical. So I made my picture 4 bytes wide. And on that stack, the bottom of the stack is up on the ceiling at the top of memory. See that? That's the highest number. And then it grows downward. In order to keep track of what's happening on the stack, there's this thing called the stack pointer. See that thing over there, ESP? And it's pointing over there right now, 434.100. It's pointing over there. What it happens to be pointing at, well, look over there, char star A, that little guy there. Oh, and I've got the wrong address in there. Sorry about that. Let me fix it. That should actually be a 4 in there, so it matches the rest of my slide. There we go. That came out of our main function that was sitting over here. See that? Main A equals. So that's pointing over to those letters sitting on the stack. It's a local variable. and it's growing down. In fact, when the getUs function gets called, look what happens. The stack pointer has moved way down there, and it's added some other things onto the stack. What it's added on here, I've got in yellow, it's added on first a return pointer. The return pointer is, after you finish running this, where do I go? That's what that is. And then we've got this thing in green, that's called the save frame pointer. For our purposes, it's not terribly important to know what that is. What it's for is keeping track of where the stack pointer was before I did anything. Because while a function's running, it could allocate more or less memory, it can move all over the place. When it's all done, it wants to clean up its mess. So I kind of need to know where I started. So usually the first thing done in a function, in assembly, is it stores where that thing is. It's a bookmark. Now below that, I've got 4, 8, 12, 16 little boxes. Remember that when I define that function, look at that, char C16. How big is that array? 16 bytes. And that's what that is. So that C is pointing where that thing starts. And let's imagine the user types in the word hello. Then we're going to get the letters H-E-L-L-O. And see, we're going from lower memory toward the top. It enters it in that way. And then the rest of that is all empty. There's nothing in there. Everything's fine as long as they just type H-E-L-L-O. Before I move on, there's actually a really important thing here that I just need to mention to you. I want you to notice that there's another value I'm tracking up at the top. The ESP is keeping track of where the stack is pointing right now. But that other thing, the EIP, that's called the instruction pointer. That's how the computer knows this is the next thing I'm supposed to do. When it does it, it moves that along and says, that's the next thing I'm supposed to do. Like an actor following a script, it's what line I'm on. It's what I do next. When we called a function, we said that current thing, that pointer, gets stored on the stack. And there's a very curious thing here that you may have noticed. Notice that, for instance, I'm currently pointing at 09AEF002. See that? But when you look at the yellow box toward the bottom there, well, halfway, A8E7AE09, that doesn't look anything like where that other one is. Look more closely. It actually does look similar, but it's backwards. It's actually, look at that. I'm going to read from right to left. You ready? 09AEE7A8. Hey, that's actually pretty close. What's the deal? This is the hardest thing we're going to talk about all night. You ready? Our computers are Intel-based computers, and they're not alone in this. There's other ones. They're what are called little-endian computers. What's that? I'm sure you've heard that before. What is that? Little-endian or big-endian? Well, you know what? You and I, we are big-endian. I'll prove it to you. I ask you to write a number down. I want you to write 1024. Tell me, which digit do you start with? How many start with the 1? You put the big end in first. 1024. You work from big to small. We're big-endian. It's easy for us. It makes sense. The computers we use are little-endian. Guess what that means? They put the little end in first. So here, the little end of that value is the A8. And the big end of it is the 09. So it has simply written that backwards. Now, don't worry too much about that. That is the hardest thing we'll cover. And that only comes up one more time tonight. So just file that away. We actually have enough information here to actually see a stack exploit happen. Watch what happens now. Previously, we entered H-E-L-L-O. Let's imagine, though, that I enter in a whole stream of capital A's. So you see, as they start getting stored there, A, and then I switch to 4 ones. Because a capital letter A, if you take a look at it, the hexadecimal value of that is a 4-1. So I'm just switching over. Now, when I go from the BFFFFFDC, when I start there and go up 16 bytes, we're fine. But when I keep on writing, now I've overwritten the save frame pointer, and then I've overwritten the stored return pointer, and then I overwrote the value of A. What's happened? I have smashed through, it's actually called smashing the stack. I've smashed through the save frame pointer. I'm overwriting stuff in the stack. That's a bad thing. Because when this function finishes executing, it's going to want to use that value up there at the F4. It's going to want to use that to figure out where to go. But I've changed it. I changed it with junk. But what if I were able to put in there a value for an address I control? That's the essentials of doing a stack exploit. So let's experiment. Let's see it happen. We're going to now find a flaw and see if we can create a working proof of concept for it. To do that, we're going to use a very basic technique. Now, there are much more advanced techniques. For instance, if I wanted to figure out what the flaw was in the RDP service for Microsoft, what I would do is I would take the patch that they're issuing, and I would either reverse engineer the patch or do a binary difference, the patched versus the unpatched service, and figure out what they did. That's a lot harder. But fuzzing is really easy. If I know there's a problem in how it handles input, I could just start fuzzing the input. All that means is I'm going to jam junk in there until I can make it break. If I can cause its behavior to change, now I've got something I can scratch at until I can get it to do what I want. For us, we have a simple network service that's going to be listening on port 7777. I've created this service specifically for the demonstration here because sometimes I've seen these demos and they really are very contrived. If you run this command line tool with this option and with the debugger, and that's not how we really do exploit research. So instead we have a network service that's multi-threaded, which actually makes it more challenging if you wanted to follow this in a debugger. But we don't need to do that. We don't need to disassemble it. We don't need to examine memory. Nothing. It turns out that exploitation is very easy. So let's see how this works. I just simply want to make it change its behavior. Let's take a look at this service. So over here somewhere, hold on. Over here, I've got a Unix machine running, and this machine here has this service. It's called server. And all I'm going to do is get the thing started running. There it goes. It's waiting for a connection. Then I'm going to switch over to another console window, and I'm going to connect to it. Now, I could use Telnet to connect to it, but I prefer not to. The main reason is that Telnet, it actually is not a clean connection. Telnet sends control codes and other kinds of things, and I don't want anything interfering with what I'm doing. So instead, I'm going to use the tool Netcat, which creates a very clean connection. There's nothing extra. And tell it to connect to my machine on port 7777, where the service is. The service comes back and says, hello, enter your command. And it echoes it back. Now, this is not fancy, right? It's not a real service. It's just for the demo. But I can now experiment with this, and I'm trying to see if I can change its behavior. Now, there are fuzzers I can use to automate this. Things like Sully and other kinds of cool things that I can program to automatically manipulate this for me. But before I ever go there, because that actually requires a lot of work to set up, the very first thing I'm going to do, and this is just from experience, is I'm going to say, you know what? If they're saying there's a buffer overflow condition based on the input, I'm just going to jam stuff in there. Forget about 5 or 10 characters. Let's just go crazy. I'm going to use Perl and tell Perl I want to print. How about we go with the our favorite, the capital A, and I want to print 20,000 of those. I mean, why not? If there's a buffer overflow, right? Let's go with 20,000. And I want to send that through Netcat to my machine on port 7777. Boop. And I'm looking for a change in behavior. Has there been a change in behavior? What is it? No response. It says hello. It says command. I never see receive. I never see the data come back. There has been a change in behavior. Now, before you got here, I did do something with my machine, and I would do this on a system where I'm doing this kind of research. What I've done is set a thing called the U limit for core dumps to be unlimited. And what does that mean? Well, if I take a look in this directory, you'll see that, at least I think you will. Hold on. Did I not kill it? Where's my core dump? Maybe I didn't do that before you got here. Let's try that again. Let's start the server, and let's just rerun that same command. Oh, look at that. Now I've got a file called core. So by default, this system is not going to create core dumps. What's a core dump? A core dump is something really bad happened when I was running, and I'm going to stop running now, and I'm going to put a copy of my memory on the disk so someone can look at it and see what went wrong. These are not generated by default these days. The reason is because that memory image, it's just dumped. What if there's sensitive data in there? Well, it's just sitting on the disk now. It's unencrypted. You can just have at it. So we generally don't create them by default. But there's actually a downside to not creating them. I want you to notice over in this window, did the server die? Did the server die? Well, I'll tell you what. Have I restarted the server? Since I got it to dump core, have I restarted the server? No. Netcat 127.0.0.1. Is the server still running? That means that without the core dumps running, would I have any indication on my system that that server is having a problem and someone's trying to exploit it? No, there's no indication because this is a multi-threaded thing. One of the threads died. And that actually makes it more challenging because I can't just run it in the debugger because it's spawning threads off. The main thread didn't die, it's a subthread. I personally prefer to have core dumps turned on and have a job watching my system to see if core dumps appear. Because if a core dump appears, something needs to be patched and someone's doing something bad. But now I've got some early warning for that, right? Now there's risk associated because if someone breaks in, of course, now I've got this RAM sitting on the drive. Something to think about. It's a possibility. Maybe I'll have core dumps, but that ulimit command that I set to be unlimited, I could set the core dump to be 1,000 bytes. So I'm limiting how much data is in it. Anyway, now that I have that core dump, here's my next stop. Now don't let this scare anybody. I'm going to use GDB. It's a debugger. But we are not going to look at any code. Don't worry. We're not going to have to step through memory, nothing crazy like that. I'm going to tell GDB to open up a core dump called core. When I do that, it tells me why it died. It said that program terminated with signal 11, a segmentation fault, which means you try to read or write memory that you do not have the right to read or write. It's out of your process space. What memory did it try to access? 0x41414141. Does that sound familiar? Those are capital A's. That's what I sent. Perfect. I now know that whatever I sent, it ended up crashing through the stack and overwriting that return pointer. I can control execution path. But now where is that return pointer? That's the next question. While I'm here, though, I'm going to take a look at something else. I'm going to ask it to show me the current registers. And there are two registers I'm really interested in. I'm interested in this one right here, ESP. ESP is currently set to BFFFE980. And I would also be interested, of course, in the fact that the instruction pointer got modified. I just want to file away the FFE980, E980. because what I want to know is if that changes. One of the protections that exists these days to prevent people from compromising your stuff is randomization of your address space and where your stack shows up. I want to know if this program's using that or not. Now to find out, here's what I'm going to do. I'm going to stop this thing, delete the core. I have to remember to delete the core because it's not going to create a new one. Delete the core and restart the server. Then I am simply going to run the same command again and look at the core. What does ESP look like? The same. Is this process randomizing its memory space? Perfect. That makes my life so much easier. Now, if it was randomizing the address space, it doesn't mean it can't be exploited. It just means I have to do it a different way. That's all. What kind of different way? Well, one way I could do it, I could use this thing that's gotten a new name. There was an older name that I can't remember now, but it's called ROP, Return-Oriented Programming, for instance. Using return-oriented programming, I could build a stack frame of my own with a return address into a standard library. Now, that's not normally how you call things. You usually call them, but I can return to them too. That's fine, as long as I have the right things on the stack for that to work. That's a great way to do it. And there's other ways to do it too. Finding something in memory that doesn't move. The Linuxscape process was a great way to do that for a long time. So it doesn't make it impossible, it just changes my technique. Seeing this though, I can use a very straightforward technique. I can put my code right on the stack. But to do that, I have to figure out where exactly that return pointer is. Now, to do that, we could go the hard way or the easy way. What do you guys want to do? I like the easy way. Let's give that a shot. So I am simply going to exit out of the debugger. I'm going to remove the core dump. I try to have a habit of remembering to do that. I'm going to restart the server just in case there's something corrupt there. And I just want to take a look at what my IP address is. I am at 111.147. The reason I want to know that is we are now going to switch over to this super handy tool called Metasploit. Now Metasploit you've probably heard of. It is an exploitation framework for which there is actually very poor documentation. Sorry about that. I'm not involved, but I'm sorry. They actually made this decision a few years back that HD, at least privately, will tell you maybe it was a bad idea, but they decided to switch the whole thing over to Ruby. It originally was written in Perl. And in switching it over to Ruby, I think that they were planning to make or take advantage of this excuse Rubyists or Ruby programmers use. See, their excuse is Ruby is self-documenting. When your programmer tells you the language he uses is self-documenting, what's he trying to say? I'm not writing any documentation. That's what he's saying. Now we're going to look at some Ruby in a little while, and I'm going to ask you if it looks self-documenting or not. I'm not convinced. But anyway, they said self-documenting. So there's like no documentation for this thing. If you want to figure out how to generate a new exploit with it, you got to go digging through Ruby libraries to figure it out. However, it also has some really handy tools that come with it that people who use Metasploit all the time, sometimes they aren't aware these things are here. Like there's two we're going to take a look at. In the tools directory, there's this thing called pattern create. The way it works is you feed it a size. You can also feed it other stuff too if you need to, but a size. Now, I think we use 2,000 characters. If I use 20,000, if I use 20,000, it'll like scroll way off the screen. So I'll stick with 2,000. It's a little more controlled. But it creates this pattern of stuff. Well, who cares? What's the value in that? Well, watch this. I'm going to tell it to create a 2,000 byte pattern and send that 2,000 byte pattern using netcat. 147, is that right? 147. Send it to that host on port 7777. So it sends that pattern. Okay, you say, who cares? Well, If I come back over here, I have a new core dump. And if I look inside of that core dump, notice that it tells me here is where that program failed, the thing it tried to access that it couldn't. It is no longer all capital A's. 41346541. Now I'm probably going to have to come back to that because I'm not going to remember it. But let's see what we can do. 41346541. So I'm going to come back over here and use a second tool, pattern offset. 0x41653441. Did I get that right? No. 413465. There we go. I think that's right. And I'm going to tell it that came out of a 2000 byte pattern. And when I press enter, it says, oh, that's 132 bytes. So now if you wanted to, the hard way, I could sit here with the debugger and I could dump out RAM and figure out where the stack is and then start counting 1, 2, 3, 4, 5, 6. Man, I hate doing that. Isn't that easier? 132 bytes. Now what do I do with that? Well, we are actually ready to start creating our proof of concept. So I am again going to delete my core dump and restart the server. There's a lot of that happening. It's just part of exploit development here. And I'm going to start assembling the pieces I know. What I know right now is that the distance from wherever this buffer starts, how big is the buffer? I don't know. I don't care. But I know that from where the buffer starts to where the return pointer is, that's 132 bytes. So I need to put some padding in here because that's where now I can start changing that return pointer. All right. So I'm going to use my friend Perl. I'm going to tell it, hey, Perl, could you please print for me? Now, we could actually put anything here. I'm going to put NOPS because that's traditional. But, actually, we don't need to. I can put capital letter A's. It just doesn't matter. And I'm going to tell it, could you please put 132 of those into a file named padding? And if all goes well, that file should be 132 bytes long. It sure is. So it looks like we're in good shape so far. All right. So that's going to take me from where input starts to the return pointer. Next, I need to pick an address to return to. That sounds harder, doesn't it? Well, wait a minute. Remember that stack pointer? It didn't change. I think it was BFFF E980. And what that was telling me was that after it tried to return, that's where the stack pointer was. That is the next address on the stack. You know what I'm going to do? I'm going to again tell Perl, hey, listen, could you please put the value, now the value I want is BFFF E980. That's the value I want. I want it on the stack. I have to write that out as binary stuff. So I'm going to be using a \x but what kind of system is this? Little endian. What does that mean? That means I need to put the little end of this number. It has to go in first. The little end is the 80, and then the E9, and then the FF, and then the BF. Are you okay with that? All right, so I'm going to stick that number in there. I'm going to say, I would like you to put that into the return address, just a file called return. And how big should that file be? 4 bytes. 4 bytes. I'm good so far. I like to do it in pieces. Could I create one massive command line that does all this stuff? Yeah, but then if it didn't work, man, that's going to be a nightmare to fix, right? So I like to do it in bits. So all right, so I've got the padding. I've got the return address. It's ready to go. What else do I need? Well, I need some shellcode. I need something to do. Now, for a proof of concept, you do not have to get creative and go generate your own shellcode and learn assembly language. You don't need to do that. Because it turns out that there are repositories of shellcode out there on the internet. You just help yourself too. This one here, this little bit of shellcode is all that's necessary to open a shell, to open a command prompt. That's it. This is all you need. It's written in this case using the AT&T assembly syntax. Not important. We don't need to take it apart. All I need to do is compile it. To compile it, we're going to use what might feel like a weird command. We're going to use GCC. GCC, what's that? That's a C compiler. C compiler, that's assembly code. You know what? It turns out almost every compiler you use compiles to assembly language and then compiles that to machine code. So many of our C compilers actually will understand assembly. In fact, you know what you can do in C code and C++ code? Inline assembly. It knows how to do it. So I'm going to tell it, I want you to compile that. However, I only want it compiled to machine language. I do not want it to try to make it a runnable binary. I don't want that because it's not one. So I'm going to add an option, a -C option, that says just assemble it. When I do that, it creates a file called shellcode.o. Now I can actually find out what the object code looks like. There's this tool called objdump, and if I give it a -D for disassemble, it'll show me, now on the right, that is exactly the same shellcode we had, but on the left, see those bits, those hexadecimal values there? That is the equivalent machine language, which I do not have to read, I don't have to understand, nothing. In fact, we're using this without even understanding the assembly. I don't really need to. I just know I need to get this assembly to run. Now what I need to do is take those bytes and put them in a file. Now I could do that by copying them manually, which is prone to error. I'm not so great at that. Or I've got a little tiny script here called obj2bytes. And if I simply run that against that file, it creates this file. All it has done is extracted the machine language, and it ends up being 28 bytes of code. I can even prove to you it's the same code. If I do ndisasm, it's a disassembler I have installed here, against that code, I'll tell it's 32-bit code, against shellcode.o.bin, the code we get back is exactly the same. So it's just converted it to machine language. That's it. There's a cool thing here, by the way. I teach a secure coding class for C and C++ programmers, which is actually a pretty important thing because how much of our stuff is written in C and C++? Now, before you answer that, I know you're thinking, well, we use Java. How many of the libraries your Java thing is relying on are written in C and C++? Everything's written in C and C++. This is a pretty important thing. And in talking to programmers, you know what? There are several bad things they do. One of the bad things they do is, I need a buffer to store some stuff the user's going to send me. I don't know what they're going to send me, but I know it can't be more than 512 bytes. So they'll just randomly pick some magic number, 512. That's how big the buffer is, which is exactly what leads to the problem we're having with this piece of code. It's got a buffer overflow in it because they didn't never think they'd send you more than that. We've got tons of problems with this stuff. And one of the issues with the programmers is, and I actually do a demo like this with them, is, well, but that buffer is so small, you can never do anything useful with it. How big is our shellcode? 28 bytes. 28 bytes. That's not very big, right? And you know what? If I had to, I could get that down to around 12 bytes. You don't need a lot of space to make bad things happen. Anyway, we got 28 bytes of stuff here. So at this point, I've got all the pieces I need. Let's assemble them. I'm going to take the padding, followed by the return address, followed by the shell code, and I'm going to put that all into a single file called exploit. It's just gluing them together one after the other. And I end up with a file that is, all told, 164 bytes long. Now, if all goes well for our proof of concept, okay, the server is running, cross your fingers, I'm going to cat exploit through netcat to my machine on port 7777. Nothing came back. What's happening over here? What? There's a shell running. Oh, I don't know if that's okay. What's going on there? Well, let me exit out of that shell. Where am I now? Now, when I do that, this connection goes away. But if I connect to that service again, it turns out that server is still running. Where was that shell? It was in the server. Now, here's a really awesome thing. What don't you see? There's no core dump. Oh, that's awesome. Because now there's no trail, right? Now, you can't always do that, but it worked out in this one. We cleaned up after ourselves in our shellcode, and no problem. There is a little downside to my current exploit, though. See, I can run the server here, remote machine, and then on my machine where I'm running the exploit, I can get it to pop a shell over there. That's disappointing. But this is just a proof of concept, see. All I needed to do was prove that I can get it to execute code. And once I can do that, now we can introduce Metasploit. But you know, I'm looking at my watch here. It's almost 5 after the hour already. Do you think there's enough time? Let's switch back on over here. Did I leave the server running? Let's just make sure. Yeah, server's running. Let's come on over here, and I'm going to open up in a text editor the modules directory of Metasploit. I'm opening that up, and I'll make this bigger, because inside of modules is where everything is, like all of the exploits. And inside of there, I've got a folder called private, where I keep my private reserve. And I've got a file called sample. Now, let me zoom this guy in. This sample here, remember I said that they're not great at documentation because they say, oh, it's self-documenting. See? I mean, it's really obvious what that does, right? What the heck is that? That's Ruby code. There's no documentation to tell you what to do with this stuff. So what I did is I took a little time, and I took an existing exploit, and I chopped out everything not necessary, so I ended up with a template. And now I just have to fill in the blanks to create a working exploit. Let's see what we have to fill in. Now, name, my first exploit, description, San Diego. I mean, now I don't really have to fill those in, right? I'm going to skip down. Let's just do the ones I have to do. All right, it wants to know how much space do I have to put a payload in? The answer is not 132. 132 is the distance from the beginning of the buffer to the return pointer. I put my code after that. And I told you that the stack tends to be toward the top of memory. And we were at BFFF E980, E980. So I've got E980 up to FFFF. I've got that much space. But I'm not really good at multiplying 16s in my head. So I'm just going to pick a number here. I'm going to say, I'm going to bet there's at least 256 bytes there. Now, if I get this wrong, if it doesn't work, I'll go back and do the math on it. But I'm going to say E9 to FF, that's got to be at least 256. I think it's actually more than that. I think it's a couple thousand, right? All right, so we'll go with 200. Yeah, it's a Linux host. Let's see. Return address. Oh, yeah, I need that one. 0x BFFF E980. Right? Offset. Oh, 132. Remote port. 7777. Guess what? We're done. Let's save this guy. It's going to be called, let's call it, what do you want to call it? 60 minutes. How about that? 60 minutes. Close that guy up. And now let's start Metasploit. Now I just had to fill in a couple of values, right? It can't be that easy. Let's see. It takes a little while for it to load everything. And this is one of the reasons they questioned whether Ruby was the right way to go. Okay. Use exploit private 60 minutes. All right. Set payload. Now this is the beauty of Metasploit. See, I know the values. Now I want to know what to do. The payload? Well, I'll double tab. And when I double tab, it shows me all of the Metasploit payloads that will fit in 256 bytes that match a Linux machine. And I can pick any one of them and add it on. I'm like strapping the warhead on the missile here. So let's use Linux, x86, or let's do shell, bind, TCP. In other words, I want to get a shell. Show options. Let's see. I need to set the remote host. That's going to be that host right there. Exploit. Oh man, that only took like 4 minutes. Only took 4 minutes. In fact, you know what? This whole demonstration took less than 60 minutes. And what did we do for most of the time? What did we do? We spent the whole first half hour doing what? Hey, here's what a stack is, and we store stuff in memory, and then we spent like 20 minutes coming up with the proof of concept. And once we could prove that it could be done, it took us 4 minutes to turn it into a working exploit onto which I can glue any Metasploit payload. This was just a shell, but that can include the interpreter. Who's doing a pen testing class or something like that? How cool is the interpreter? You guys been talking about that? What can I do with the interpreter? Anything, right? 4 minutes. Are you patched yet? How you doing with that 30-day patch window, right? Now, all right, admittedly, the one we did was for a demonstration, right? It wasn't a terribly hard one. There is a class that's actually being taught here. We've got 660 and 710. These are exploit development security researcher classes. And one of the awesome things, awesome, you know, not so good for security people, but one of the awesome things that you find out is that for every single protection that is being developed to prevent malicious code from being exploited or executing on your system, there was a paper written about 5 years ago that explained what those developments would be and how to defeat them. We're still catching up on the protection end. We are behind. It doesn't matter how you want to protect it, there's a way around it. Now, if you want to learn how to do that stuff, Steve Sims' class and the one Jim Shoemaker, I think he took up, that is the best exploit development class I've ever seen. It's really super. If you're interested in taking it, there's actually an assembly fundamentals and reverse engineering class that we've got running in Vegas for 2 days before the conference. They give you like half off of that. If you need to brush up on assembly, is anyone doing the 660, 710 thing? Anybody? No? Okay. You should already know assembly before you show up there. And sometimes people show up, they're like, oh yeah, I've done that. And then they're like, oh yeah, ooh, it's been a while. So we got a little refresher there if you need it. If you've got programmers that need to learn to write secure code, we got a class for that too. If you're interested in this, if you want to, wow, that was pretty cool. I want to show someone that. I've got a website out there, auditcast.com. I know it doesn't sound like exploits, but I've got a recording of this up there along with links to the server code if you want to take it and you want to reproduce it and try that yourself. And if you run into trouble, you need a hand, feel free to send me an email. Now there's more bad news. The bad news is that all our host defenses, they're a waste of time. So let's talk to Rob Lee, because he's going to get up here and he's going to tell us how all of those things are getting defeated forensically. Come on up, Rob. I'm done, man. You're on.